Calculus PC, Lesson 1.3, Exponential Functions. So also a lot here, as I keep saying for each one of these lessons. Hopefully you've seen it before. We'll go through it fairly quickly. An exponential functions defined in a lot of ways. My favorite definition is f of x equals a times b to the x. And that's the one I try and keep in my mind at all times because it works best. The a value is the initial amount. If you know why, great. If you don't, I'll show you later. And the b value is the rate of growth or decay. And again, we'll talk about that a little bit later. Those are the two types of exponential functions. Growth, the b value is greater than 1, and decay, the absolute value of b is less than 1, which is nonsense. 0 is less than b is less than 1. We don't really put negative b values in, but again, a lot of people like to write it that way. So let's do a graph, see what it looks like, and then of course do the domain and range. So the original exponential graph looks like this. It hits here at 0, 1. So this one should hit there, but it's down 4. So 1, 2, 3, 4. So it's going to hit here. And I know that because if I put in 0, I get 3 to the first. 3 to the 0 is 1, and 2 minus 4. I forgot about the 2. Got to start with the initial amount, go down 4. Minus 4, 1, 2, 3, 4. It's still going up like this. It's going up fast. I mean, I can just throw in a number, see where it takes us. Put in 1, 2 times 3 to the first is 3, 2 times 3 is 6, minus 4 is 2. So we're going to get something like that. The asymptote, the horizontal asymptote up here is at 0. It was at 0, now it's down to 4. So you can actually dot that in. And it looks something like that. Domain is all reals, negative infinity to infinity, and the range is negative 4 to infinity. And if you just look at the graph, you can figure that one out. So practice on that coming. Just for the fun of it, let's graph another one and find the 0, which we don't usually do. But hey, let's try something different. So got a negative 2.5 this time. So putting a negative out front flips things so that they go from top to bottom, which we'll talk about in a second. And then the plus 5 moves that asymptote up. Put in 0, we get negative 2.5 plus 5. So 1, 2.5 about here. Sorry, my bad. Negative 2.5 to the 0 is 1. Well, 2.5 to the 0 is 1. Negative 1, so we'd hit here at 4. And then where does it hit over here? Well, I threw it in the calculator, and I could do an intersect function. It's going to look something like that. And we're going to get to logarithms eventually, so we might as well start with now. 0 equals negative 2.5x plus 5. 2.5x equals 5. Take a natural log of both sides. Could have taken a log base 10, doesn't really matter. X comes down out front. and throw it in the calculator. We get about 1.76, and that's pretty close and accurate with our graph. So we'll be playing with all these things. These are things you're expected to be able to understand. If not, always ask questions. Whenever I do exponents, I like to quickly go through and say, yeah, multiplying is adding, dividing, subtracting, taking to a power is multiplying. A couple of keep you on your toes problems: add, 7, multiply, subtract, and then take it to a power. And we could actually, a lot of people like to distribute this. I have no idea why. And don't forget, you can write things with negative exponents, top to bottom, bottom to top, all that good stuff. So how do we model an exponential function? Lots of ways to do this. I'm going to check 290.4 over 287.9. See what I get. I get 1.009. And I'm going to try a couple other ones. Here I get 1.0010, and the last one I get 1.009. So I will go with a B value of 1.009. I'm going to call 2002 year 0. And so on and so on, so that my initial amount is 287.9. So here is my quick and dirty 287.9 times 1.009 to the T, where the 2003 is year 1, 2004 is year 2, and stuff like that. Now I also threw this into the calculator and did an exponential regression, and we've done a linear regression, so it's the exact same thing, and it gave me y equals 287.8, 1.009 to the T. So you can see it's actually not a bad approximation. It worked out fairly nicely. The calculator is always going to be more accurate, but sometimes we don't have one handy, and sometimes we need to do a quick check. So the population today, if the year 2002 is 0, then the year 2015 is 13, so T equals 13. 287, I'll use the calculator one. 287.8 times 1.009 to the 13th. We should have about 323 million. People in the United States today, which is interesting. I don't know what it is off the top of my head. I think it's a little bit higher than that, a little bit lower than that, but it moves so fast and things change so much, it's a tough call. But that's what exponential growth is. So what other ways can we model exponential growth? Well, we can use the letter E, which we'll talk about a little bit, and that would be the principal amount times e to the RT, or just to the T, depends. More on that later. For money, simple interest, which works, is going to be the amount is the initial amount times 1 plus the rate to the T. And for compound interest, the amount is the initial amount, 1 plus r over n to the nt. N is the number of times compounding. And compounding just means when we check the interest. If I'm doing simple interest, I'm technically just looking at it at the end of the year. And if I check it at the end of the month, I check it at the end of a day, that's what compounding means. Hopefully you've seen that before. And a half-life is how long until there's half. And what that means is if I have the simple interest formula, A equals original, and you say, no, I'll start with $1,000, then you would end up with 500, 1 plus r to the t. And you wouldn't even bother doing that after you've done enough problems. You would just do this. I'm going to divide both sides, so I'm going to do that. Half-life. Simple enough. So let's look at the increase in U.S. population. It looked like it was increasing by 0.009% a year. So we could use the simple interest formula there if we wanted to model. And we could say the number of people is the original amount, 287.9, 1 plus 0.009 to the t, which is effectively what we did. Just another way to look at it. And that E thing we talked about, that means continuous growth. And the world population is not growing continuously. I mean, there's a baby, there's another baby, there's a death, there's another death. So you would be able to say it's discrete. There's little chunks of it, but it's happening so fast and so often we can actually consider it continuous. Chemicals are also discrete, but there's an uncountable number of atoms and molecules that are all interacting, so we consider that continuous, and continuous works really, really well. The fun thing is that we can use a little formula here to calculate it. I put in 2, I get 2.25. If I put in 100, I get 2.705. If I put in 1,000,000, I get 2.71828. And for those who know what E is, that's pretty close. That's accurate to 5 decimal places. That's E. So you're going to have to get used to practicing with E again. We'll talk about it more as we go forward. It's huge in calculus. Natural log, which is based off of E, and E are both used a lot in calculus. So be prepared. Happy mathing.